Hello everyone, welcome back to our course on abstract algebra. Today we're going to talk about a different, once more, another type of subgroup of a symmetric group, which is the dihedral groups. We've talked about symmetric groups, we've talked about the alternating group, and now we talk about dihedral groups, which is sort of like closing a chapter in our lives, because we started talking about symmetric groups because we were talking about symmetries of polygons. So what are precisely, the question now is, what are the symmetries of a regular n-gon? And remember that by symmetries we mean rigid motions of, in this case, this polygon, a rigid motion that will preserve the shape. It will preserve the position of vertices and sides, and it preserves distances and angles, but it can move, the shape can move and end up sort of in the same position. So for example, well, we can see what are the possibilities for this polygon. If I have a polygon, I can number my vertices 1, 2, 3, etc. up to the nth vertex, and I want to know what kind of rigid motions I can do of this polygon, and you can actually determine what all of those are because, well, let's just see where one goes. One will go where, let's say, I'm going to just write the positions again here, 1, 2, 3, 4, etc. And let's write here the kth position, and let's assume, let's see now where one went, and suppose that one lands here. Okay, so one is sent to the kth position. Then, because it's a rigid motion, we can determine what motion it is as long as I know where 2 is. There's going to be two options. 2 could be here, it has to be next to 1, or 2 could be here. So the question is, where did 2 land? So we have two options for these rigid motions. One is being sent to the kth position, and then 2 can go to, it has to be, because it's a rigid motion, it has to go to either k plus 1 or to k minus 1. And then these conditions determine everything. The rest, where 3 goes, where 4 goes, etc., these are going to be determined by those two conditions. And now you can see then that if I call these symmetries, we know they form a group under composition. These are bijections of the vertices to the vertices with a certain conditions of the rigid motion. So this is what we are going to call the symmetric group of the regular n-gon. And this symmetric group has how many possibilities? Well, I can send one to any vertex. So you see that I can send it to n vertices, any of them. So there is n options for 1. And then for 2, there are 2 options. Either I go to the next one or to the previous one, and that is all. So there is precisely 2 n possibilities. And notice that these can be represented as elements of Sn because they are precisely there are 2 options. If I have 1, 2, 3, if I name all my vertices, I just need to determine where 1 goes and where 2 goes. So 1 goes to k and 2 goes to k plus 1, and then I know that k goes to k plus 2, etc., and then it will cycle, and at some point n will go to something else. Or the other option is 1, 2, 3, n is the one that goes to, 1 goes to k, this goes to k minus 1, this goes to k minus 2, until I reach 1, and then it goes to n, and so on and so forth. But you see how where 1 goes and 2 goes determines where everything goes. So that's why there is exactly 2n elements. So this is a group, and this group is what we call the dihedral group, Dn. So let me write it down in the next page. The group of symmetries of a regular n-gon will be called the dihedral group, and I'm going to call it Dn because it's for n-gon. Okay, there is in the literature, some people call this, they would call it D2n. So I'll explain in a second what this all means, but and we've just seen that Dn is a subgroup of Sn with 2n elements. Okay, we'll see some concrete examples in a moment, but what I want to do first of all is the following. This is our first example of a presentation of a group, and is the following: that Dn abstractly for some n bigger or equal to 3, of course there is no 2-gon, the 3-gon is the smallest such example. The subgroup or the group Dn abstractly is generated by R and S, 2 elements, R and S. R is for rotation, and the other one is for reflection, but we call it S, such that R to the n is 1, S2 is 1, and SRS is R inverse. What does this mean? What this means is that Dn is any possible combination in these letters. So, for example, elements of Dn will be R and S and R squared, R cubed, up to R to the n minus 1, and then R to the n is 1, so that is the identity element. And then we can have other elements such as RS or SR or SRS, but this one is R inverse. And we actually see that, notice that because R to the n is 1, this is R times R to the n minus 1, and that tells me that actually R inverse is R to the n minus 1. So I already have R inverse in the powers of R. So I don't get something new by doing SRS, and so on. So we'll see in a second what are in fact all the elements, how all the elements can be represented like this. But that is essentially what the theorem is saying. The theorem is telling me that Dn is generated by 2 elements, so words in the letters R and S, with the conditions that R to the n is 1 and S to the 2 is 1. So let me prove this theorem. Okay, so let's do this proof. What I'm trying to prove is that the symmetries of a polygon with n sides of a regular n-gon are really generated by R and S. Some element R whose nth power is 1, some element S whose square is identity, and that they satisfy this relationship. So let's start by identifying what's R and what's S. What are they going to be? So I can draw a polygon, and here is my n-sided polygon, and here is 1, 2, 3, etc. And notice that there is a map that sends 1 to 2, which is a rotation by 2 pi divided by n radians. That rotation is a symmetry, is a rigid motion of the polygon, and sends 1 to 2 and 2 to 3. Great. So that identifies what element I'm talking about. So R is going to be rotation by 2 pi divided by n radians. And if so, then what is r to the k for some power k? That will be the composition of r k times. So it's r k times. And that will be rotation by 2 pi n times k radians. In particular, if I go all the way to n, then I get a rotation by 2 pi n divided by n times n. So it's a 2 pi radians, which is a full circle. So it is the identity symmetry. So r to the n is 1, so that's going to be my r. Now, what is another element that is going to play the role of s? We have this other element. Here is again my my polygon, and then I have a line that bisects my polygon and that goes through 1. Okay, and this one, what it's going to do is, well, is going to do a reflection about that line. So 2 ends up here, 1 stays put, but n ends up here. And that is going to be, as then is going to be a reflection about the bisecting line through the vertex 1. So that is a reflection, and therefore you can see that then, because it's a reflection, if I compose it with itself, I get that this will be the identity. So now I have 2 elements. So I have R and S that are part of the N. And next, what I need to do is, and such that, by the way, R to the N is identity, and S squared is the identity. So next, I need to show you that they actually generate every single possible symmetry. So now, remember that every symmetry of regular n-gon is of the form, well, there is either the one that sends, let's write the polygon like this, and there is one that sends 1, 2, 3, and 1 is going to go to the kth position. So 1 ends up here, 2 ends up here, n ends up there. And that one, you see that 1 is being sent to 1 is being sent to k, 2 to k plus 1. So it's also a rotation. And note that r sends 1 to 2. So r squared sends 1 to 3, and r to the k sends 1 to k plus 1. So this one that I'm writing here is actually r to the k minus 1. It sends 1 to k, right? Because then r to the k minus 1 sends 1 to k, and that is one of them. So every symmetry is one of 2 forms, this one, or a second form, which is that this is sent to, so this is the kth position, k plus 1, k minus 1, and 1 ends up here, but 2 ends up here, and n ends up there. How do we get that one? Well, let's see how I can make it happen using R and S. So to do that, what I'm going to do is first a reflection and then a rotation, because see what happens if I start, I'm going to do a composition of 2 of these maps. So here is 1, 2, 3, n, 1, 2, 3, n. 1, 2, 3, n. And I'm going to start first by doing a reflection. And the reflection sends 1 here, but 2 ends up here, n ends up here. So this is n minus 1, and 3 ends up here. And then I want to rotate it. So 1 ends up in the kth position. So I'm going to use my r to the k minus 1th map. And that is going to send, well, is going to, if you keep going and we draw where k is and k plus 1 is and k minus 1, now 1 is going to go here, but because 2 is trailing, 2 is behind it, and n is above it. So that is sending precisely the polygon where we want it, you see? So this one over here is S composed with r to the k minus 1. So what we've shown is that thus every element, let's say sigma, of the dihedral group is of the form, let me write it actually in the following form, is either r to the k minus 1 for k between 1 and n. For k equals 1, I get the identity element. For n, I get to the rotation by 2. It's the last rotation before a full rotation, or of the form r to the k minus 1 s, also with k between 1 and n. And we've shown that everyone is of that form. So in particular, we have shown that Dn is of the form, all the elements are 1 r squared up to r to the k up to n minus 1, and then s and rs and up to r to the n minus 1s. And you see that those are, there is n elements here, there is n elements here, so in total there is 2n elements, and that's all of them. And that in particular means that it is generated by r and s, that the elements r and s under multiplication generate all the dihedral group. Great. And r and s satisfy the properties that we want. R to the n is 1 and s squared is 1. One more property that we have to show is that s r s is equal to r inverse. So to do that, what I'm going to do is again draw what is happening when I do SRS and what happens when I do R inverse. So let me draw my polygons. So what happens, I start 1, 2, n, 1, 2, n, 1, 2, n, 1, 2, n. I'm going to start with S. Okay, I'm going to start my trip with S. With the reflection, 1 is here, 2 is here, n is here. Now do a rotation. When I do the rotation, 1 ends up here, n is here, 2 is here, 3 is here. And then do S again. When I do S again, now what happens is that 1 is here, 3 is here, 2 is here, and n is over here, and 4 would be over here. And that is the same from here to here. What map is that? What's happening is that 1 is going counterclockwise. 1 went here, 2 went here. So what's happening is that I'm going 2 pi over n radians counterclockwise, but that is precisely the inverse of r, so it's r minus 1. Let me write it with this color. So this shows that yes, S, R, S is R inverse, and that finishes the proof of the theorem. Okay, so let's do an example of a dihedral group. I'm going to explicitly write all of D4, which are the symmetries of a square. 1, 2, 3, 4. So what are the possible symmetries? Our theorem tells me that the symmetries, the symmetric group on the square, is a set with 8 elements generated by rotations and reflections. There's a rotation by 2 pi divided by 4. So that's a rotation by pi divided by 2, so by 90 degrees. So there is 1, r squared, and r cubed. Those are the possible rotations by 90, 180, 270 degrees. And then there is a reflection about the line that bisects the square, and it goes through 1. And then we saw that the other elements are rs, r squared s, and so on. So what I need is, just write rs and r squared s and r cubed s. And in fact, we see that now these are exactly 8 elements. So those are all the elements in D4. Let's see what those look like. We know what the rotation has to look like. It's going to send, 1 is going to end up here, and then 2 ends up here, and 3 ends up here, and 4 ends up here. So this is the rotation, r. And I can write it as an element of the symmetric group. So as an element of the symmetric group, I know where 1 goes. 1 goes to the position where 2 was. 2 goes where the position where 3 was, and 3 goes to the position where 4 was, and 4 goes to 1. So it's this element. Now, what is the one that is given by reflection? So the reflection is about this line, more or less, and then 1 and 3 are going to stay put, and then 2 and 4 are going to switch up. So what element is that? 1 stays put, 3 stays put, and 2 and 4 switch. So it's this element, which is just 2, 4. So as a subgroup, D4 as a subgroup of S4 is generated by 2 permutations, which is a subgroup generated by 1, 2, 3, 4, and 2, 4. So I can actually write every single element of D4 in this way. So the identity is the trivial cycle. What is R is 1, 2, 3, 4. And I can compute R squared by doing it twice. So it's 1, 2, 3, 4 composed with 1, 2, 3, 4. I can multiply and see that 1 goes to 2, 2 goes to 3, so 1 goes to 3. 3 goes to 4, and 4 goes to 1, so this cycle closes, and then 2 goes to 3, and 3 goes to 4, so 2 goes to 4, and 4 goes to 2. So it is the product of 1, 3, and 2, 4 as a product of these joint cycles. R cubed, if you do the same thing again, or if you do it as a rotation, you can see that that is the 1, 4, 3, 2 element. S itself, we just seen that is 2, 4. And then RS will be 1, 2, 3, 4 times 2, 4. And you can compute that yourselves, and that is 1, 2, 3, 4. So check that part. R squared S is in fact just 1, 3. And R3, R to the 3S is 1, 4, 2, 3. So if you put all of this in a set, this is D4 represented as a subgroup of S4. And now you can check that this is in fact a subgroup of S4. So if you do any other product of these cycles or these elements of S4, then you can see that this is closed under multiplication, and there are inverses and so on and so forth. So it is indeed a subgroup, and it's a quite interesting subgroup of S4. S4 has 4 factorial elements, but D4 has only 8 elements, so this is not all of S4. Okay, so that's as much as I wanted to do about symmetric groups, and then next time we'll start talking about cosets, which will allow us to prove a very important theorem called Lagrange's theorem. So until then.